Well, I'm going to talk about delivering thermal comfort in summer, and more specifically, the role that exposed concrete soffits can play in doing just that. Everything I'm going to talk about is covered in a lot more detail in this publication. So, the use of exposed concrete soffits really started to become popular in the UK back in the late 90s. And at that time, there was a whole series of owner-occupied headquarter buildings that were constructed, all to a sort of common design format, built over 3 stories with a central atrium, and each featuring exposed soffits, which formed an integral part of the cooling strategy. Now, since then, this technique has found its way into more mainstream construction, including speculative offices. There's a few examples here. And the reason why it's proving so popular is its passive performance. And just a quick lesson on building physics and physiology. We actually lose about 60% of our body heat by radiation and only 40% by convection. And in order to be able to lose that 60%, we need to be able to physically see other surfaces around us which are cooler than we are, so that we can radiate heat to them. Obviously, heat goes from hot to cold. And the soffit is ideally placed for that purpose because, firstly, it's not very far away, and distance is important. The closer the surface, the better. Secondly, it obviously has a very large surface area, and that's very helpful too. Thirdly, it doesn't tend to get covered up in the same way as floors and walls do. And fourthly, if it's made from concrete, it's going to have a high level of thermal mass. And what that means is that it can absorb an awful lot of heat without actually warming up itself. In other words, the soffit temperature may only vary by about 2, maybe 3 degrees over the course of the day, even though it's absorbed a lot of heat. So we can continue radiating body heat to that surface throughout the day. Now, we do, of course, have to get rid of that heat, and that's generally done at night by ventilating the building, opening the windows up, letting the cool night air in to draw that heat back out of the concrete so that the next day it can once again absorb heat via radiation. Now, the other reason why they're proving so popular is because, of course, it's a passive system, and that allows us to save an awful lot of energy in CO2 and minimise the use of air conditioning. And this graph just gives you a rough idea of the sort of savings that can be made. So here we've got data from CIBSE, and that large green blob shows you the CO2 emissions from a typical air-conditioned office, and that's in kilograms CO2 per metre squared each year. So it's in the range of about 125 to 200. Now, a good practice office with really energy-efficient chillers, good solar shading, etc., you can bring it down to around 75 to 100. And then the kind of buildings that I'm talking about, so your heavyweight concrete building with your exposed soffits, may also have some form of active cooling as well, which is quite common. That type of building, you'll get your CO2 emissions down to around 30 to 50 kilograms per metre squared, so a massive reduction. There's lots of ways of doing it. I'm going to talk in a minute about the simplest system. I'll start with that, which is just a plain flat soffit. We've also got more complicated systems, which are both passive and active. So you've got perhaps water-cooled soffit, or maybe a combination of exposed soffit with mechanical ventilation. So these are just other ways of boosting the cooling output and regulating the temperature. So I'm going to run through these really quickly, and I'll show you a few little case studies as well. So the simplest option is just to have a plain, flat, exposed soffit. And if you use that in combination with nighttime ventilation, which I spoke about just now, you'll get around 15 to 20 watts per metre squared of cooling from that soffit. So that's radiant cooling. You might get on top of that another 40 watts or so from natural ventilation, from having the windows open. But of course, that depends on the weather and the air temperature outside. So it's a pretty modest cooling output, but it's enough to ensure a comfortable environment and prevent overheating, providing you've got a low occupant density and fairly low internal gains. I'll show you an example of a building that uses this technique. National Trust headquarters in Swindon. A south elevation, very well shaded. That's important to give the exposed soffits a fighting chance. Got to keep the solar gains out. And there's a view of the soffit in one of the office areas. It's pretty unremarkable. These are precast concrete units, painted with white emulsion. That's a pretty standard finish, and very simple light fittings. Now, this particular building also has mechanical ventilation, which is mainly used during the heating season, but can also be used during the summer months as well. If you've got still conditions and you can't get enough air through the building at night, you can use the mechanical ventilation as well. Okay, next system, very similar, except now we've got underfloor mechanical ventilation. And what this does is to straight away double the surface area of the concrete through which you can get heat in and out during that 24-hour heating and cooling cycle. So you can take much better advantage of the thermal mass. You can reach much greater depths because you're going in from both sides with your heat. And for that reason, you can get up to 35 watts per metre squared. And in this particular example, it's a coffered slab, doesn't have to be. And the reason you introduce a coffer, I don't know whether you know this, but it's essentially to reduce the self-weight of the concrete unit, which in turn means you're going to have larger spans. But it also has the added benefit of increasing the surface area of the soffit underneath, so you get more heat in and out. And that helps contribute to the slightly higher cooling output. So this particular system is used in all of those HQ buildings I showed you at the beginning. And this was one of them, Toyota headquarters in Surrey. So they've got precast concrete coffered floor units, very high quality finish. And they've actually cast in lots of rebates, which you can see there for all the services, so for the lighting, the extract grills for the mechanical ventilation, smoke alarms, that sort of thing. The frame of this building is in situ concrete, so it's a mixture of precast and in situ. Okay, next system, Terminex system. This has been around for many years and at one time was the only off-the-shelf solution available. There are now quite a few of them. So far it's been used in, I think, over 300 buildings in the UK, so it's well proven. And basically it takes a standard hollow core precast floor unit and then it's modified so that you can get air passing up and down these cores, and I'll show you how that works. So you take a standard precast unit, you then drill out the webs for 3 of the cores. It's every 3 and 5 that's used generally, so that the air can pass between them. So it's your mechanical supply coming in here, fresh air going up and down, and then it enters the room through a hole in the soffit with just a simple diffuser on it. So you've got really good heat transfer with this system between the air and the concrete, which is why you can get, as it says there, up to 40 watts per metre squared. And you get particularly good heat transfer at the corners where the air's going around the corners because it's nice and turbulent, which is what you want. Most of the cooling is still radiant from the soffit in the way I described, but you also get obviously some convective cooling now from your fresh air supply. And it's a really good year-round system as well. It's good at recycling heat gains in the winter, so you hang on to them and preheat the fresh air the next day. And as I said, used in loads of buildings. This is just one of them, Jubilee Library down in Brighton. This is the south elevation, and you might think it's a lightweight building. It's actually an extremely heavyweight building, a lot of concrete, and a lot of glass on the south elevation for good daylighting, and also for some passive solar gains during the heating season. And I don't know if you know about passive solar design, but it works very well with heavyweight buildings because the thermal mass can soak up those solar gains and recycle them later in the day. But I'm not going to talk about that. I'm just going to show you one of the perimeter reading rooms. Again, fairly unremarkable, just a plain, flat concrete soffit. Those are the hollow core units. You can see one of the supply diffusers on the underside for your fresh air supply. Simple suspended light fittings with acoustic wings, and that's a very standard feature in all of these buildings. You probably noticed it in the Toyota building I showed you just now. And the reason you have those is because obviously the soffit, concrete soffit, is a very hard surface and tends to reflect sound, and your reverberation time can be a bit high if you don't have something to absorb some of that sound. That's what the acoustic wings do, and they're very effective. It's a very standard feature. Okay, next system, getting slightly more sophisticated now, and this is where you're using embedded pipework to regulate the temperature of your soffit. So here we've got plastic polybutylene pipework. And in this particular example, it's in what's called a lattice girder slab. And this is where you've got a precast concrete biscuit, which forms your soffit. It's very thin, so that's produced at the precast factory. The pipework's embedded as part of the process. And it's delivered to site, craned into position, and then you've got an in situ concrete topping, which is this bit. And these spheres, if you're not familiar with those are plastic spheres. They're hollow. They're called void formers. And you put those in to reduce the amount of in situ concrete you need and to reduce the weight of the unit. And a bit like the coffers I mentioned earlier, if you reduce the weight, you can have larger spans. And they're right in the centre of the slab, so they're not in any areas of tension or compression, so they don't affect it structurally. Now, I'll show you an example of a building that uses precisely this system, which is the business school at Manchester Metropolitan University, which was opened a few years ago. And here you can see one of the floor units at the precast factory. The concrete's cast onto a steel bed, that's that shiny surface, and it gives you a really good surface finish to your soffit. And you can see there the reinforcing and the plastic pipework that's been tie-wrapped to the reinforcing. That's ready for the concrete to be poured now. And when it is, some of the reinforcing will still be protruding, and that will be covered up by the in-situ concrete on site. And there is one of the units being craned into position. These are quite deep. They're 475mm deep. And you can see they've actually used polystyrene void formers instead of those red plastic spheres. So a very deep unit, but they managed to get a 12-metre span, which is pretty good. And that's what they look like once they're in position. Very, very high-quality finish on this project. If you look, you can see that the perimeter columns are reflected in the soffit. Gives you an idea of the finish. And they've actually used a blend of 75% white cement and 25% ordinary Portland cement for the precast units, and gives a very light finish. Did add a bit of cost, but overall they actually saved money on this project because they found that they didn't need to paint the soffits with white emulsion, which is what a lot of these projects have. And here's a slightly more recent example of a building that does exactly the same thing, water-cooled soffits, just fair-faced finish, no paint at all. And it's the White Collar Factory in London, which was completed last year. And if you want to know more about that, we've got a really good write-up in our ecobuild brochure, which we have copies of over there, so do help yourself to one of those. Okay, moving on. Next system is essentially the same from a thermal performance point of view. Same pipe work, same cooling output. What's different now is it's embedded in just a simple hollow core, precast hollow core slab. And the advantage of that is that it's slightly cheaper than the system I just showed you, the lattice girder system. But you do get a slightly more utilitarian finish for the soffit. It's a little bit rougher, but generally it's absolutely acceptable, especially once it's been painted. And Vanguard House uses this system. This is up in Cheshire. Got a BREEAM Excellent Award when it was opened a few years ago. And there you can see the hollow core units having been craned into position. And these ones are unusual, actually. They have something called top strand reinforcing, which ensures that the units are absolutely flat. Normally, hollow core slabs have a little bit of camber in them, which sometimes you can see when you look up, but not on this project. And you can see all the plastic pipework sticking out there. That's all ready to be connected up to a distribution manifold, which will be hidden in a bulkhead along with the steel beam. And that's the end result after it's been painted, which I think is a pretty acceptable finish. Now, one thing just to say about this project and also the business school is that the water comes from an aquifer, so they've got a borehole. Comes up at about 13 or 14 degrees, which is an absolutely ideal temperature for cooling the soffit. If you had it any cooler than that, you run the risk of getting condensation forming on the soffit, which would be really bad. But 13, 14 degrees, absolutely fine. And the other thing you can do is to link it up to a heat pump, which both of these projects do. So you can boost the temperature during the heating season, and it becomes a radiant heating system. So it's pretty much a year-round heating and cooling solution. And again, you can see light fittings with acoustic wings. Okay, final system. This is where we've got chill beams on an exposed soffit. Very popular in new build, but also extremely popular in retrofit projects and refurbishment projects. You get a lot of cooling from a chill beam. It's all convective. So having it with an exposed soffit works really well because that's radiant cooling. So you've got a nice combination of the two, which makes for a more comfortable environment. And as it says, you can get up to 160 watts in total. Now, The reason why it's popular on retrofit projects is if you've got an old 1950s or 60s or perhaps even 70s office building, concrete frame office building, the slab to slab height is not always that generous. And during the refurbishment, you probably want to put in a raised floor, which wouldn't have been there originally. So that just sort of compounds the problem. But to compensate, you can strip out the old false ceilings, make good any sort of blemishes in the concrete, give it a coat of paint, put in some low-profile multi-service chilled beams. So that gives you your extra cooling. It also provides your lighting, houses your smoke alarms and smoke detectors. So it's a really neat package solution. And as I say, it's low profile, so it doesn't really impact too much on the floor-to-ceiling height. Very, very quick example of a project that did just this. Conquest House, concrete frame building in London, built in the 1950s. They did exactly what I said, put in a false raised floor, stripped out the full ceiling, put in some beams, and I think they managed to maintain a 2.7 metre floor-to-ceiling height, which is pretty good. And this is now used by an international business school. I think I'm out of time, so as I said, if you want to know more, do have a look at this publication. There's lots more case studies in there, and there's a few other systems, slight variations on the ones I've shown you as well. So thank you very much.